Okay, so we've been talking so far about vectors. Now let's actually get the calculus into the vector calculus. So if you're finding the derivative of a vector function, you've got some vector r, which is in respect to t, and you've got x, y, and z, or I, j, and k components. Assuming all of those parametric equations, x, y, and z are all differentiable, then the first derivative, which can be represented as dr dt, r dashed of t, r dot of t, you just differentiate each of those parametric equations with respect to t. So we've got dx dt attached to y, dy dt attached to j, and dz dt attached to k. And we can see that's represented on our formula sheets here. They don't have every representation. They don't have the r dash and the dr dt. They've just got the r dot, but it is important to keep that in mind. And also, just above it, a nice reminder of how to find the magnitude of a vector. Now, second derivative, you do the same thing again. You differentiate each of those individual chunks with respect to t. So we can see r double dash. That could have been written like this. Sorry, I said double dash, I meant double dot. Or you could have d squared r dt squared. Now, some properties of this. If you take the derivative with respect to t of a constant vector, so a constant vector would be something like, so here's some constant ai plus bj plus c k. If you take the derivative of that, dc dt, you're going to get 0i plus 0j plus 0k, because they're constants. And it's important to note that's the zero vector. It's 0 with the tilde, the squiggle underneath it. It is not the same as 0, the scalar. I know it might seem the same, but it's got to end up in a vector. Therefore, it's got to be the zero vector. Similarly, when we've done derivatives in the past, if you have some constant k, you could take that outside the derivative and just pop it there and then do the derivative as you normally would. If you are adding together two of those vector functions and you're differentiating with respect to t, you could individually do each of those and add them. Doesn't matter if you add them first, then differentiate, or differentiate first, then add. Doesn't matter. And if you have some function which is dependent on time, f of t, multiplied with rt, then you'll notice we've got a bit of chain rule action going on here. We've got the original function times d dt of that function r, and then you differentiate f of t and then multiply it by rt. And f has got to be a real valued function. Let's actually do some examples. First one's from the Cambridge textbook. We've got this vector function here, starting off nice and simple, and we want to find r dot of t. So cos goes to negative sine t I. Sine goes to positive cos, so we've got negative cos t, because we already had that negative there, and that's j, not I. And then 5tk just becomes 5k. Differentiating all of those bits again with respect to t, so r double dot t. We've got negative and sine goes to positive cos, so we've just got that negative out the front there. Cos goes to negative sine, so that becomes plus sine tj, and that last component, 0k. You could technically have not written that and just had a two-dimensional vector there, but I'm just doing it for an abundance of clarity. So that was using a parameter t. We can also use theta as our parameter instead, but the same rules all apply. So let's look at this exam question. We've got a curve is defined by the parametric equations. X is a function of theta, and we've got y as a different function of theta. And we want to find the gradient of the curve when theta is 7 pi over 6. So gradient of the curve, remember, that's going to be dy dx. That's our definition of the gradient. So in order to find that, we have x as a function of theta and we have y as a function of theta. So what we're going to have to do is use the fact that dy dx is going to be dy d theta times d theta dx. So let's separately find dx d theta, then we'll use that reciprocal trick and we'll find dy d theta as well. And we'll do that second. Now, just a little note, if you wanted to write that as this vector function, that would have been cosec theta plus 1i plus 2 cot theta j. So just a two-dimensional vector here. Okay, I'm going to go quickly through this actual derivative bit because this is a little bit of revision, but dx d theta is going to be negative cos theta over sine squared theta double check my algebra there. dy d theta should be negative 2 sec squared theta over tan squared theta. Okay, just checking those answers on the CAS, and remember tan squared theta plus 1 is equal to sec squared theta. Okay, we're all good. So to find dy dx, we're going to, again, we said dy d theta, which was that negative 2 sec squared theta over tan squared theta. And we're going to multiply that by, we want d theta dx, so that's the reciprocal of this. I'll pop the negative out the front because it doesn't matter whether it's on the numerator or denominator. So we've got sine squared theta on cos theta. And I don't particularly care about what that solution is because I just want to know when theta is 7 pi on 6. So because it's exam 2, let's actually do that on the CAS. So for that we want this one. And we want to multiply that by the reciprocal of this one. So you could do this using fractions, but I'm just going to use that one. And let's use the given. It's in Math 3. We know that theta was equal to 7 pi over 6. Okay. Great. So we get negative 4 root 3 on 3. And you'll note in the solutions, they don't rationalize the denominator. They would have had negative 4 on root 3. If you look at the exam paper, you can see that this question isn't really about vector calculus. However, the techniques that we've just applied are relevant. And I just found it a nice example of reviewing a little bit of implicit differentiation and also reviewing gradient of a curve, looking at the derivatives and things like that. So it all relates together to things we've done previously. Let's have a look at another example. Okay, we have an interesting vector equation here where we have in terms of t, but we've also got Euler's number in there just for a bit of fun. We want to find r dashed of alpha and r dot alpha and r double dot alpha, so first and second derivatives, and we're told, so in order to do this, we're going to have to generally find r dot of t, and later on r double dot of t, and then we'll start looking at that alpha value. So the I term is going to be a bit boring. Derivative of e to the power of t with respect to t is just et, and then we're going to have, here we need to use the fact that we've got something inside of the brackets. It's a function, so we're going to have 3, bring the power down the front, et minus 1, subtract 1 from the power, and we're going to multiply by the derivative inside there, which is et. So e to the power of t, I mean. Let's put these together. And we need that j there. There we go, now it's vector. Okay, first term when we're doing r double dot is pretty boring. The second term gets interesting. Firstly, we're going to have that 6et and then et minus 1, and that's to the power of 1. And then we're also going to have 3et minus 1 squared, and that's all the j component. Okay, now let's look at that alpha value. It says r at the particular point alpha, point corresponding to the endpoint of the vector, that equals, well, if we substitute it into this original one, we're going to have e to the power of alpha I plus e to the alpha minus 1 cubed plus 1 bracket j, and that needs to equal I plus j. If we equate coefficients, this e to the alpha, the coefficient of this I, needs to equal the coefficient of this I, equals 1. And the only way that's going to be true is alpha is 0. So that means the question's asking for r dot of 0. And substituting it into this one, we're going to get that I term, it just becomes 1 because e to the power of 0. And then we've got, here we'd have 1 minus 1, so that all goes away, it's 0. So it's just I. R double dot of 0 substitute it into that, looking along, see how we've got that e to the power of t minus 1. That j term's again going to become 0, so it's just going to be that I term again. Great. Equating coefficients coming in useful as always. So we've got a curve is described by this vector equation here, and we're told t has to be in between negative pi on 2 and pi on 2. That can happen. So we want to find the gradient of the curve at the point xy, and we're told x equals sec t, y equals tan t. Well, they didn't even need to tell us this bit because we can see that these come from that. So didn't actually need that, but thanks. So we want to find dy dx. But we have those parametric equations, x and y are both in terms of t, so we're going to have to use that implicit differentiation again. dy dt times dt dx. So actually go ahead and find dx dt. If x equals sec t, then that's going to be sine t over cos squared t. And dy dt, tan t, so it's just sec squared t. That one's just from the formula sheet. So going ahead and continuing this one, that's going to be sec squared t was dy dt, and the reciprocal of dx dt, because we need dt dx, is cos squared t over sine t. So that's going to be 1 over cos squared t times cos squared t over sine t. They cancel nicely. 1 over sine t, you could have written that as cosec of t. That's better. So find the gradient of the curve at the point xy. So that's just a general point. And now we want to find the gradient of the curve at this particular parameter when t equals pi over 4. And that's inside of the region that we are interested in. Okay, so dy dt at this particular point means we're just going to be, a reminder, this was dy dx. Oh, and we're finding dy dx, because that's the gradient, remember? So dy dx when t equals this value, it's just going to be cosec of pi on 4. And remember, that would be 1 over sine of pi on 4, so that's going to be 2 root 2. Or if you rationalize, you could just write it as root 2, but remember, irrational denominators are fine. Okay, we've been looking at derivatives. Now let's have a quick look at anti-differentiation of vector functions. So if we've got our vector function here and we're going to integrate both sides with respect to t, we're going to take those individual components and we're going to integrate them with respect to t. And oh, I feel like my brackets are not looking super nice. Oh no, they're okay. These match up. So we are individually going to integrate each of these components. Similarly, how we could individually differentiate, we can anti-differentiate similarly, and then we're going to get, this is defined as the derivative of that gave us our original x, so it's saying that is what happens when you anti-differentiate lowercase x as a function of t. And you're going to get some constant vector added on the end, and as a reminder, constant vector, if you derive it, it's a zero vector, not a scalar. Now, the constant vector is going to look something like this. You're going to have an I, j, and k component. Let's call them cx, cy, and cz. Sometimes you'll see it written, instead of having these x, y, and z, and then the c component, they'll actually put those c components inside. In fact, I think that's probably more often how you see it. You put it inside so you have all of the I components together, all of the j, and all of the k, rather than having a mishmash of both. So let's look at some examples of it. Okay, in this one we're told the second derivative of r is given by 10i minus 12k. And we want to find r dot of t, and because we want a specific rather than a general solution, they've given us an initial condition. So we know r dot of t is going to be the antiderivative of r double dot t with respect to t. So we're going to have 10 dt I plus, we've got nothing for the j, and we've got minus 12 dt k. So 10ti minus 12tk. You could skip that step in the middle in future. And we still need a c. We need that constant of integration. Now, in order to find what that value of c is, recall the initial condition that they told us. They said when t was equal to 0, we had it equal to 30i plus 20j plus 10k. So that means as r dot of 0 equals 30i minus 20j plus 10k. Notice if you put r of 0 in here, t goes to 0, t goes to 0 here. So that therefore will equal c. So putting it all together, r dot t, let's put all of the I bits together. So I bits, we have this 10ti, and this value of c was 30i. So putting that together, we could have 10t plus 30i. Now let's put together the j components. There's just this j component. We don't have anything in here. So that means we're just going to have minus 20j. And now let's put together the k components. So that's going to be plus 10 minus 12t, all multiplied by k. Okay. Okay, now we want to find r as a function of t, and we've got this initial condition ready to go. So r is going to be antiderivative r dot t dt. So that means we're going to have integral of 10t plus 30 dt in the I direction minus 20 dt in the j direction plus 10 minus 12t dt, and that's going to be in the k direction. You can skip that step if you feel you don't need it. So that's going to become 10t squared over 2, so 5t squared plus 30t, and that's all multiplied by I, minus 20tj plus 10t minus 12t squared over 2 will be 6t squared k, and don't forget your constant. I'm going to call it d. You could of course use c subscript 1, c subscript 2. So our initial condition was r when t was 0 was equal to 2k. Therefore, notice every single one of these terms has a t attached to it. So that tells us that c's got to equal 2k. Now, just a reminder at this point, you might find yourselves lapsing into your previous scalar calculus work. C is a vector. It's going to have multiple components. In this case, it's just got a k component, but it could have I, j, and k. It's not just going to be a scalar constant added on the end. It's going to be a vector. So putting that all together, we only have to worry about putting this into the k bit. Everything else doesn't have a constant vector added to it. So let's keep with the color coding because I find it was helping. So we're going to have 5t squared plus 30ti. Still going to have minus 20tj. And then the k's, oh, what color am I going to choose now? I don't know what I haven't used. Let's use pink and go for a clash. So we're going to have plus, we've got that 10t minus 6t squared plus 2k. So there we go. Nice to put it in terms of I, j, and k all grouped together. We're told that r double dot of t is negative 9.8j. That sounds very free-fallish to me. Looks like j is the vertical direction here, and that looks like r double dash t. It's the second derivative of a position vector, so that's telling us about the acceleration. So this very much looks like a free fall question here. We've got some initial conditions. Good, we need 2 because this is r double dot of t and we want to find rt. So each time we anti-derive, we're going to need an initial condition or some sort of point to substitute in. So let's start So we just had that j component. Remember, it's like we had a little 0 dt I there, which is still 0 I. So don't have any I components involved yet. Nearly forgot the critical thing. Let's put in a c. Now, a little note about the last question. I used two different values of c to indicate that there were two different constant vectors added on the end. That's good practice to get into. Don't use c for one thing in one part of a question and another thing in a different part. Distinguish them somehow. I nearly said differentiate them. Distinguish them somehow. So, r dot of 0 was 30i plus 40j. Okay, so that's telling us, therefore c, that t would go away, so that means c is going to be 30i plus 40j. So r dot is going to be, I component is just 30i, and now we've got two j components, 40 minus 9.8 j, and that's 9.8 t. Okay, last one. Now to find r, we're going to differentiate r dot of t. So that's going to be 30 dt I plus 40 minus 9.8 t dt in the j direction. So that one's kind of boring, just 30 ti, and we're going to have 40 t squared minus 9.8 divided by 2 will be 4.9 t squared plus different constant, let's have d. Oops, and that is just 40. Okay, so we're told that r is 0 when t is 0, so that tells us that d is therefore 0. Because each of these terms has a t, and when we substitute it, they all go away. So our general form is going to be 30 ti plus 40t. Oops, I realized that needs a j. 40t minus 4.9 t squared j. Not super exciting when the value of c, d was 0 here. The 0 vector. Now, important point. Remember we always said that needs to be a vector. So very incorrect to just say d equals 0 the scalar. It needs to equal 0 the vector. So take care. Don't make the same mistake that I just did.